So far, we have covered framing and an overview of error control as part of the data link layer. In this video, we are going to cover error detection in detail. Before we proceed, a quick quiz. As part of the error control, we saw the framework that of adding k redundant bits to the message, and we also covered the general idea behind error detection and correcting codes, that of Hamming distance, and what the design goals of some of these algorithms are. So basically you add k redundant bits to an m-bit message where k is derived through some algorithm. At the receiver, you employ the same algorithm to detect errors and take corrective action if necessary. So this is the framework on which we are going to build. A very simple error detection mechanism is the parity bit, which you must have encountered before. So here is even parity. Basically, you set the parity bit such that there are even number of ones in the code word. So here there are 2 ones, so you set the parity bit is equal to 0. So what do you think is the error detection capability of this? You think it can correct any errors? So parity bit can detect any odd number of errors because with this the parity will not match anymore. And unfortunately it cannot correct any errors because you just have one bit and it does not give you any indication of where the error has occurred. Wherever error has occurred just shows that the parity does not match. A more sophisticated version of parity is the two-dimensional parity, where you take parity of the row as well as the column. So this is also even parity. As you can see, there are 4 ones. That is why you put the parity bit equal to 0. And similarly, if you look at here, there are odd number of ones, thereby you put the parity equal to 1. So this error detection mechanism is used by the bisync protocol for ASCII characters, which are basically represented by 7 bits. So if you are working with blocks of n ASCII characters, how many redundant bits do you think you add as part of two-dimensional parity? So that's right, you use n plus 8 bits of redundancy. This n arises from the fact that for each of the n characters, you are adding a parity bit, and you are adding one parity byte for the columns that corresponds to 8 bits. That it can detect 1-bit errors is obvious given that the previous one-dimensional parity itself was able to do it. What do you think? Do you think it can correct 1-bit errors? Yes, it can correct 1-bit errors. For example, if the 0 were to get converted to 1, you will notice that this parity bit and this parity bit are going to be in error. So based on this locations, you can conclude that this bit is in error and thereby correct it. So do you think it can detect 2-bit errors? That's right, it can detect 2-bit errors. For example, if this bit and this bit were in error, you will see that this parity will capture it as well as this parity will capture it. Note that this may not be able to capture it, but you still know that it is in error. What about correcting 2-bit errors? Do you think this two-dimensional parity can correct 2-bit errors? Unfortunately, you cannot correct 2-bit errors. Suppose, let's say these 2 bits are in errors. Okay. Now this parity is fine because both are flipped, whereas you will see that these 2 parity are going to be wrong. But you really cannot tell which of the rows the errors have happened. So in general, the two-dimensional parity can detect all 1, 2, 3-bit errors and it can detect most 4-bit errors. So its capabilities are not so bad. So another error detection algorithm that is used is internet checksum. This is not used at the link layer. In fact, it's used at the network layer, and the checksum is carried over the IP header. But since it's part of error detection, I'm going to cover it here. Now, as part of this algorithm, whatever data over which you want to perform checksum is viewed as a sequence of 16-bit integers. And now all you do is add up these integers using 16 bits ones complement arithmetic. So in ones complement arithmetic, you do regular arithmetic over the bits, but the carry typically gets added back to the sum. So here is an example. Suppose these are 4-bit integers and I'm doing ones complement arithmetic. I'm just going to add them up. 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0 with a carryover of 1, right? Now this carryover has to be added back. So I'm going to add it back here. So the resulting thing is 0, 1, 1, 1. So this is a 4-bit ones complement arithmetic performed over these two integers. So what you do here is similar, except that you are doing arithmetic over 16 bits, and finally once you obtain the addition, the sum, you're going to take the complement of the result. This is the checksum. I'm going to cover an example, so that should make this clear. So at the receiver, you perform a similar calculation on the received data and compare the result with the checksum. If they don't match, definitely there is error, but if they match, very likely there was no error. Why likely? Because you can never be sure unless you know the error pattern. So here is the promised example. So IPv4 header, I'm representing in hexadecimal. Hexadecimal, each 4 bits is represented in this fashion. So this word is a 16-bit word, and there are many such words over which I want to calculate the checksum. So the first thing I'm going to do is add them up. I can potentially use 32 bits to add them up, and this is the addition result. So I have some carryover. Now this carry is added back to this sum, the 16-bit sum. So since this is a 2, the C has become E. So this is the ones complement addition over the 16 bits. Now I'm going to take the complement of this. If I take the complement of this, this is going to what is going to result in, and this is the checksum. Why am I taking a complement? That will become clear shortly. I presume people know what a complement is. So for example, if you have this, the complement of this is this. Basically flip the bits. So at the receiver, you take all the words, the 16-bit words that are part of the header, but this time you include the checksum also, and then you just add them up, basically using 32 bits. So if you did that, this is what you're going to get. So you have again a carry. Since it is ones complement, you have to add the carry back. So when you add the carry to the sum, this is what you're going to receive. So this corresponds to a 0 in ones complement. So 0 can be represented by FFFF or 0000 in ones complement. So why did we take a complement here? So taking a complement is basically negating the integer. Now when you take the complement and add this checksum back here, basically you are ensuring that the sum adds up to 0 in ones complement addition. Now comparison with 0 is a lot easier than comparison of two numbers. So that is why you take a complement here, so that once you do this addition, you can quickly compare it with a 0, whether it equals a 0 or not equal to a 0. So this is mostly an implementation artifact. So what do you think is the error detection capability of this code? Do you think it will be able to detect 1-bit errors? So this is straightforward. If there's a 1-bit error, the sum is definitely not going to match. Do you think it can detect 2-bit errors? So here is a hint. Think in terms of arithmetic. So that's right. This internet checksum is not very strong in detecting errors. For example, if you have a pair of single-bit errors, one of which increments a word and other decrements a word by the same amount, the sum is going to stay the same, and thereby it fails. Then given that it is so, it can't even detect 2-bit errors, why is it used still? For one, it is very easy to implement in software and it can detect some errors, but more importantly, majority of the errors are picked up at the link layer, the data link layer, where CRC is implemented, and CRC is a very sophisticated error detection mechanism. So all you need to capture are some residual errors, which this does fine. So we've been hearing about CRC for quite some time now, so here it is at last. So it stands for Cyclic Redundancy Check, and this is used by many link level protocols, HDLC, DDCMP, Ethernet, token ring, so on and so forth. and there is some powerful math based on finite fields behind it. So before we get to this, we need to cover some background. So I'm going to give a brief overview of polynomial arithmetic. So in polynomial arithmetic, you represent an m-bit message with a polynomial of degree m-1. So here we have an 8-bit message which I am representing by this polynomial. So this corresponds to x to the power of 0, this is x, x square, x cube, so on 4, 5, x6, x7. So as you can see, since these coefficients are 1, only x7, x6, x2 and 1 are represented. So when you're adding or subtracting these polynomials, those additions are carried over a field of integers modulo 2. That means basically the coefficients are always going to be 1 or 0. So here is an example where I'm adding x and y represented by these bits. So here 1 plus 1 is 2, but I'm taking modulo 2, that becomes 0. So remember, there is no carry here. You just start doing modulo 2. So 1 modulo 2 is 1, 1 modulo 2 is 1, 1 modulo 2 is 1. So x plus y here is equal to z. So when you're doing arithmetic over the field of integers modulo 2, it turns out that addition and subtraction are identical. Basically, it boils down to XOR. As you can see here, this is nothing but Z is an XOR of X and Y. Just to show that addition and subtraction are identical, let me do the following addition. So here I have added x plus z and what I got is y. So I'm representing it here, but if you see here, this y is nothing but z minus x. And note that x is not equal to 0. So y is z minus x and y is z plus x with x not equal to 0. That means that addition and subtraction are identical as far as the field of integers modulo 2 is concerned. So the polynomial division is very similar to integer division. So for example, if you are dividing x over y, x can be represented in this fashion where q is the quotient and r is the remainder. So for integers, this r is always going to be less than y. So for polynomials, it is similar except that the degree of the remainder polynomial will be less than the divisor polynomial. So we will cover an example later, so these things should be clear, but with this background, let's see what CRC does. So in CRC, an m-bit message is represented by this polynomial. We already saw this before. The sender and receiver agree on what is called a divisor polynomial. Now this divisor polynomial has a degree k, which is equal to the number of redundant bits that you are going to add. For example, this is an example of a divisor polynomial. So this has degree 3. That means if you are using this divisor polynomial, you are going to add 3 redundant bits. So the choice of this divisor polynomial is what determines your error detection capabilities, and this is derived very carefully based on the observed error patterns. So for example, in Ethernet, this is the CRC polynomial that is used, which is of 32 bits. So you add 32 redundant bits. In HDLC and DDCMP, you use 16 bits. So pay close attention. This is the crux of CRC. The sender sends m message bits and k redundant bits. So this is the transmitted message. I'm going to represent this by this polynomial px. So the idea here is to derive px from the message such that this is exactly divisible by cx. So when you receive a message Rx, if there are no errors, the Rx will be exactly equal to Px, in which case it is exactly divisible by Cx. But if there are errors, this Rx will not be equal to Px, and then very likely it will not be divisible by Cx. Notice the use of likely again. So it's possible that certain error patterns may result in an Rx which is exactly divisible by Cx. But as I said, your goal is to design Cx such that most common errors can easily be detected. So how do you make this Px exactly divisible by Cx? So you know mx, which is the message, you know Cx, this is given. Now your goal is to generate the transmitted bits based on the polynomial here. So the first thing you do is you multiply this message by x to the power of k. So basically you are doing this results in adding k zeros at the end of the message. So you get a temporary polynomial, let me call it tx. And now what you do is you divide the tx by cx to get a remainder. And now just subtract this remainder rx from the tx and then you get this px. Now this px is exactly divisible by cx because you are subtracting the remainder from the tx. So here is an example that gives you an idea of what is happening. 37 can be expressed as 7 into 5, 35 plus 2. Now this 37 is like this t. And let's say 5 is like this c. Now what you're doing is you're dividing t by c and you got this remainder r. Now you're subtracting this r from the remainder, so that p is going to be 37 minus 2, that is equal to 35. Now this 35 is exactly divisible by c, which is 5. So the same thing is shown here. So the tx is x to the power of k multiplied with mx. This is qx cx plus rx because this is polynomial division. This is how I'm expressing it. Now px is from tx you are subtracting rx, so this is what it boils down to. And remember, arithmetic additions or subtractions are the same when you do modulo 2, so this turns out to be this, which in turn is equal to qx cx, which is makes px exactly divisible by cx. So the coefficients of this remainder polynomial are basically the redundant bits which you add to the message bits and transmit. So here is an example that should make things very clear. So this is the message, the bits that I wish to transmit. So I'm representing it with the message polynomial. And here is the divisor polynomial. This turns out to be x cube plus x square plus 1. Note that the degree is 3, which means k is equal to 3. So the temporary bits are obtained by adding the 3 redundant bits, basically zeros at this stage, to the message. So this is the temporary thing. The temporary polynomial is obtained by multiplying the message polynomial by x to the power of 3. So that becomes 10 x to the power of 10 plus x to the power of 9 plus x to the power of 6 plus x to the power of 4 plus x to the power of 3. Now I'm going to divide this temporary polynomial by the divisor polynomial. So this is what it boils down to. So x to the power of 7, it is x10 plus 9 plus x to the power of 7. So these terms kind of cancel out. We have x7 plus x6 plus x4 plus x3. Again, I'm going to do this. It is x7 plus x6 plus x4. In fact, all these terms are kind of cancelling out. Now you have x3, so I have to do one more. So this is x3 plus x square plus 1, which leaves me with x square plus 1. So this is the remainder. So the remainder, as you can see, translates into these bits. Now I'm going to add this remainder to t, basically substitute these last 3 zeros with the remainder. So this is going to be my transmitted bits. So by the way, this division was done using modulo 2 arithmetic. So addition subtraction turned out to be the same. So here is the error detection capability of CRC. So if there were error, basically what you receive will be the transmitted polynomial and the error polynomial, where this error polynomial captures the bitmap of the position of errors. So basically if you add this, that means in those positions where there is a 1 in E are the places where the bits got flipped in the transmitted bits. Now we know that Px is exactly divisible by Cx. That means you cannot detect errors if Ex is also exactly divisible by Cx. So the goal is to design Cx such that for anticipated error patterns, Ex is not divisible by Cx. So how do we do that? Let me work out an example again. Suppose we want to design a divisor polynomial such that it can detect all instances of odd number of bit errors. Given that the error polynomial shows the bit positions where the errors occurred, and given that we want to capture odd number of bit errors, what do you think is the characteristic of the error polynomial? So that's right, this error polynomial will contain odd number of terms with coefficient of 1. Basically, wherever the bit error has occurred, you are going to have the term with a coefficient of 1, and since you have odd number of bit errors, you will have odd number of terms. Now if I were to substitute x is equal to 1 in the error polynomial, naturally since it has odd number of terms, e of 1 is going to be equal to 1. Remember, I cannot detect errors if ex were exactly divisible by cx. So given e1 is always going to be equal to 1 for odd number of bit errors, what should c1 be equal to if ex is exactly divisible by cx? So let me write this as ex is cx times some other polynomial ox. In this case, ex is exactly divisible by cx. So if I were to substitute x is equal to 1 here, this one is equal to 1. So what should this be? So that's right, c1 has to be equal to 1. If it were equal to 0, e of 1 is also going to be 0, and we don't want that. So remember our original goal, we don't want cx to be a factor of ex. So if cx were a factor, it needs to c1 to be equal to 1. So in this case, we need to set c1 is equal to 0 if we don't want cx to be a factor of ex. So now how do you design a divisor polynomial such that when you substitute x is equal to 1, it is going to take on the value 0? Basically, if it has a factor of the form x to the power of I plus 1, then c1 is bound to be equal to 0. So there you go, we devised a divisor polynomial that can detect all instances of odd number of bit errors. If I were to set cx is equal to x plus 1, we have seen this algorithm, error detection algorithm before. Which one is it? That's right, even bit parity. So remember, this has degree 1, so there also we introduced 1 bit of redundancy. Just like how we have designed a divisor polynomial for capturing odd bit errors, you can devise similar such polynomials. For example, if you want to capture all single bit errors, this divisor polynomial should have x to the power of k and x0 to be non-zero coefficients. And similarly, if you want to catch all double bit errors, cx should have at least 3 terms. This we already saw, where all odd bit errors can be captured if cx contains the factor x plus 1. And similarly, any burst of length less than or equal to k can be captured if cx includes the constant term. So these are not difficult to prove. I will leave it up to you to work it out. Another point that I need to emphasize is that CRC algorithm as such is very easy to implement on shift registers. That is why it's very popular. So here is a summary of what we have seen in this video. So it's important to detect errors, and there are many techniques for error detection ranging from the simple parity to all the more complex CRC. So going forward, we will see how to recover once we detect an error.